And I do share screen. And like that. I hope. Now you're supposed to see my, yeah, you do. How are you? It's a general question.
Great.
Great, great. Great is great. Okay, so as you've seen, I put the first problem set on the course's webpage. I will put my lecture notes there sometimes. Simply, they are very messy at the moment. So when I have some time to organize them, to make them slightly less messy, then I'll put them there. You have until next Thursday, as I promised. It's not difficult, really. It shouldn't take you that long, and I'm not going to spend that much time grading them. But it's really, as usual, it's for you to ensure that that you can follow what happens. If something is you find difficult, then do not hesitate and ask. And I repeat on saying, if you need any extension, any problem, come and ask me in advance. Don't tell me afterwards, oh, I did not submit on time, but I had this excuse. Say it in advance if you have any reason not to submit on time, because I tend not to accept requests that are coming post-mortem. Okay, so today last time we've pretty much exhausted what I wanted to say about special relativity. I actually said a little bit more than needed, but I thought that the way it is being covered in standard particle physics textbooks is simply not enough to give you a coherent picture. And there was something which I thought we can give you a better coherent picture. And now we're going to do some introduction to the standard model today, which means that we're going to learn a lot of jargon, a lot of things that, things that you might have heard of, many terms that you might have heard of, but now we'll do it in a somewhat ordered way to do things in a precise way. This is still pretty much of an introduction without getting too deep into things, which we'll go to subject by subject in the coming weeks. But first things first, so we speak about recap. I'm going to do it very briefly. We spoke about natural units. We even gave an exercise about that. We spoke about special relativity. We spoke about 4 vector, x mu, x0, x1, x2, x3, ct, x, y, z. We introduced the metric g mu nu, plus 1, minus 1, minus 1, minus 1, and the rest are 0. We introduced the Lorenz transformation, lambda mu prime nu, a transformation that transforms from one frame to the other. So, for example, boost in the x direction will be written as gamma minus gamma beta minus gamma beta gamma, and then the rest is trivial. We spoke about scalar product, A dot B. It's just A mu and B mu. So just A mu, B nu, G mu nu. I can switch the order because when I write it like that, it's an element by element. We defined the proper time, tau is the proper time. And we showed how this leads to time dilation. Then we talked about the word line, about 4 velocity, which I define as u mu. It's a 4 vector, of course. It's dx mu over the tau. And 4 acceleration, a mu just du mu over the tau. And then the for momentum, right, P mu is just M U mu. And of course the Einstein's relation, P0 is just E, but it's E over C. It's just Pi squared plus M squared C squared to the power 1/2. And I spoke about mass of a composite system and covariant derivatives. D mu is just D over dx mu. This is just dt nabla. And with the upper index, it's just d over dx mu, with mu is the lower index. So it's just dt. dt is d over dt, right? Don't get confused. It's a 4 vector. When I say dt, it's just d over dt. And then minus nabla. All right, I think this is pretty much as far as we went through, and that is definitely going already beyond what is common in classical textbooks for particle physics, but I think it's good to give you the right impression. Any questions? No questions, that means that everything is completely and fully understood. And if you're being asked in a homework or an exam,
which one is covariant and which one is contravariant?
The what?
In the derivatives? The derivatives.
The covariant, yeah, it's the opposite. This is a covariant derivative and this is a contravariant derivative. Because this is a contravariant vector, and it's the opposite. Oh, I'm not confusing. No, I don't think so. Yeah, sorry, of course. No, that's fine. Contravariant with an upper index. That's always the case.
My question is, does that upper on the derivative or upper index in what you derive by?
I'm sorry, there was some communication.
Contravariant.
Again? Covariant.
I said yes, contravariant is with upper index, but is it upper index on a derivative or on X?
No, on X it's a lower index. It's the upper index on the derivative, d mu, and this is equal to d over d x mu. X mu is with a lower index.
Okay.
Remember that if you take a derivative or divide by a lower index, it's the same as getting the upper index.
Yeah. Maybe it's more confusing, maybe it's easier. You take the upper index and you divide by it, so it becomes a lower index. Right, this is x mu with an upper index. Just, remember it like that, and that's it. Okay, are there any further questions? Okay, so we start now, as I promised you. Now we're going to start our journey through the standard model. So introduction to the standard model. So, the standard model is based on a huge number of both experiments and theoretical works. not sure where to start, right? Some people start from the electron experiment by J.J. Thomson. Some other starts later on, let's say at least in the last 80 years, which led to some comprehensive understanding of particle physics, which is unified under the theory, which is known as the quantum field theory. So it is within the framework of quantum field theory, which is somewhat unfortunate because I'm not teaching you the entire framework of quantum field theory. And I'm not assuming that you know it. So in case you haven't learned it, I'm not assuming you know it, but I will discuss some parts of it as needed, especially to give you the motivation. It does represent one of the triumphs of modern physics. There is no question. It is a great success. And there are very many thousands, or I don't know, tens of thousands, or I've got no clue how many experimental facts that some of them are possibly the highest precision ever, the highest precision measurements ever made by men. And they all fall perfectly fine within the theoretical predictions of this standard model. However, as I already said, we do have, there is a clear evidence that the standard model, for the least say, is incomplete. So there are some experimental / observational evidence that do not contradict the standard model directly, but show that there are some things which we do not understand. And here actually comes the nice connection between the particle physics and astrophysics, or to be more precisely, cosmology, because a lot of these evidential facts that the standard model is incomplete comes from astronomical observations. So in that sense, it's not that there is anything wrong with the standard model, but it's being viewed as some sort of an effective theory in a very similar way to the way we treat today Newtonian mechanics as an effective theory of general relativity, which is valid to an excellent precision at velocities which are much smaller than the speed of light. So that's the way many people think of the standard model today. And so a lot of people, the forefront of research in this field today would be to look for models beyond the standard model. We might touch a little bit upon that, but towards the end of the semester, supersymmetry, etc. I will not speak about strings because I don't know anything about strings, so I cannot teach you things I don't know. What are the evidence that the standard model is incomplete? Evidence for incompleteness of the standard model. I should say, despite the fact that it is an excellent and truly excellent theory. So I named a few. So from a theoretical perspective, there is no general relativity within the framework of the standard model. They are derived in the two parallel lines. And we know that when we get close to the place called singularity, at least one of them does not work. Possibly both of them does not work. So a standard model is derived independent of GR, general relativity, close to the singularity, not the event horizon of a black hole, but the singularity, the place where all the dimensions unify. At least one of them does not work. So this is what happens at the center of a black hole. If you want to know more, come to the GR course. Close to the singularity, at least one, maybe two. Observationally, the universe as we understand it today contains the matter that we understand. So the matter in stars, the matter in Earth, right? The matter we are made of. But there is a large part of matter which we have evidence from gravitational potential that we're seeing it, but it was never observed because it is not interacting, does not emit light. So that's why it's called the dark matter. It is not a small fraction. I mean, you'd say, okay, we do observational in astronomy, how accurate this can be, right? I mean, there is as much as accuracy we can get, but here we're talking about 5 times the matter that we have. So this has been known since the 1930s. by a very famous astronomer known called Fritz Zwicky was the first to notice that on every gram of normal matter that we can see, there are 5 grams of matter that we cannot see, but we have evidence that it's still there. So today we know that the dark matter constitutes about 26% of the matter, of the energy content of the universe. But no clue what it is. What is it made of? Now, if that sounds bad, then this is a smaller problem, because about 70%, actually 69%, according to recent measurements, of the energy contents of the universe is what is called as dark energy. This is something whose origin is even less clear than that of dark matter. Essentially, we know that the universe expands, and this kind of makes sense if you think of it as starting from the Big Bang. But the discovery, which dates back to 1999, so only 21 years ago, it turned out that the universe is not only expanding, but the expansion accelerates. There is something that pushes it to expand. And this is something nobody has any clue what it is. And apparently when we were making measurements, it turned out that 69% of the energy context of the universe, energy in the universe, this is what we know as dark energy. And really people got no clue what it is. Which means that the matter that we actually do know, so all the standard model and all this theory that we're going to describe really accounts for only something like 5% of the entire energy content in the universe. So the matter we know of, or we understand, is only 5% of the energy in the universe. There's something very big out there that we don't really understand what it is. So this is another problem, which tells us that the standard model cannot be complete because it's only account for 5%. The other discovery, which also was awarded a Nobel Prize a few years ago, something like 15 years ago, possibly, I'm not sure exactly when, is the neutrino masses. So there are these particles called neutrinos, and in standard model, they are supposed to be massless. But going back to the 1960s, I think there was the first experiments that showed that the neutrinos oscillate. It goes back to Raymond Davis Jr., which means that they change their flavor. We'll discuss about that shortly. And this can explain the model of the sun. And however, the fact that they oscillate, they cannot do that if they are massless. They have to have some mass. So experimental evidence I think the Nobel Prize was in 2007 for that. Don't take my word for it. The discovery was made in the 60s, and it took them about 40 years to give the Nobel Prize for this. Experimental evidence show that neutrinos do have mass. which is not exactly understood in the framework of the standard model. Another very important question, which again relates to the looking at the universe, is the asymmetry between matter and antimatter. The theory will describe the Dirac equation, if you've heard of it. If not, I'm going to teach it to you. Predicts that there would be equal amount of matter and antimatter in the universe. Of course, we know that this is not the case. Right, we live in a universe made of matter, not of antimatter. There are two M's in the symmetry. Made of matter, not antimatter. So there must have been something that broke the symmetry, or there is something that means that the theory is incomplete. Within the framework of the standard model, there is no such mechanism that can explain the observed antisymmetry. So these are observational evidence. There are other problems that are, they are not the problems per se, but it just kind of, there are things that seems to be added ad hoc to match experiments. So it's just added down. Now, some features of the standard model seem to be added ad hoc, which is sort of, motivates theorists to look into that there might be something more fundamental that we're missing there. So I just I go briefly over that. So there is this, what's called the hierarchy problem. Hierarchy problem. So in the standard model, this is something which we will learn. There is a special particle which is called the Higgs boson. And what makes this particle so special is that this is the mass. This is the particle that gives the mass to all the other particles by interacting with them in a process which is known as spontaneous symmetry breaking, SSB. So SSB is called spontaneous symmetry breaking. This is a process in which the particles gain their masses by interacting with the Higgs field of the Higgs field. Gives masses to all other particles. However, when you do these calculations, it's normally done in a perturbative way, and because you get quantum corrections. And what happens is that when you do it, the quantum corrections becomes very, very large, which means that the mass of the Higgs that you have to start with has to be very much fine-tuned, such that it will cancel all the corrections that appear there. So it's really require fine-tuning of the Higgs mass. Now, you can always say, okay, so this is like that, right? So fine, but fine-tuning is never something that the theorists like. You like something which is robust. So that hints that there might be something there that, it's not a coincidence that it happened to be like that. It might be something deeper that we don't see. That's one thing.
What do you mean by the Higgs mass has to be fine-tuned? Isn't it given by nature? It's a constant of nature, so you cannot play with it?
Yes, but when you do yes, it is a constant of nature, but the theory, if you had that the mass of the electron would be slightly different, you still end up with the same theory. Right? Correct. We live in.
You say it all breaks down?
Yeah. It all breaks.
If we had discovered the Higgs to be a little bit heavier, the world wouldn't exist according to the standard model, something like that?
Yes, it's not that if we haven't discovered it, we discover it in a given mass. Nobody knew what the Higgs mass is. The problem,
Right.
because of
No.
the corrections you had to do, there is this thing called a bare mass, and it has to be fine-tuned exactly to this value. Okay, otherwise the universe would collapse in a sense. We'll speak a bit more in depth about that later on. So, you know, just to give you the impression, fine-tuning is not something we like. We don't like a universe that depends on a very fine-tuned parameter. The other issue, of course, is which relates to that. You know, in the standard model, there are 19 free parameters. It looks like an odd and big number. You know, we like a theory with a small number of free parameters, right? You know, in Newton's gravity, there is a gravitational constant, right? The speed of light. Here we have 19 free parameters. It just like looks like just looks too much. You know, there's not that there's anything wrong with it. It just looks too much. So that motivates people to think that there is something deeper with less free parameters that we are missing. And the other one, again, it's a bit technical. It's called the strong CP problem. So CP is called charge parity. We'll talk about that as also charge parity symmetry. Again, this basically relates to the question of why we have more matter than antimatter. It is expected that a term that breaks this charge parity symmetry would exist as part of what's called the strong force. But so far it was never found. So maybe people haven't looked to high enough energies. That's a possibility. Maybe there is something more than that that is not known. Okay, so far I've discussed the problems, but now let's discuss the model itself before we're going to discuss the problem. So just this to give you to be honest enough to tell you that, look, this is, there are very many interesting problems here that are still waiting for their solutions. Okay, and a lot of people, you know, thousands of people, I don't know how many billions of dollars and euros are being investigated in CERN, essentially to find answers to these questions, precisely to these questions. In CERN, of course, other places. So the standard model is based on a quantum field theory, right? Is defined by the Lagrangian. And the Lagrangian, in turn, is defined by its symmetries. How much time we have to go deep into the investigating the symmetries, I don't know at the moment. We'll have to see how things evolve. I'm not going to describe to you all the symmetries of the Lagrangian, not now, maybe later. Right now, I'm just going to discuss the physical outcome. So the physical outcome of all that are particles. The physical outcome of this, you know, entire mathematical structure is really the particles. The physical outcome of the mathematical structure are the particles. That exist in the standard model. Needless to say, all these particles are detected experimentally. We know that they exist, they have been seen. So basically, we divide the particles in the standard model into three categories.
Related this point, I have a question.
Yeah.
Is it that all the particles that are predicted by the standard model have been detected, or was the Lagrangian written so that it includes all the particles that we have detected? So what?
No, all the particles that have been predicted in the standard model had been detected. The last one that people searched for in years was the Higgs, and it was found, I think, in 2012, less than 10 years ago.
So people knew it existed before it was detected?
Yes, wow. Higgs predicted its existence back, Higgs and Eggleston predicted its detection back in 1963, I think.
Okay, but besides the Higgs, is that true for all particles, or were they already, like,
sorry?
Besides the Higgs, is this true for also for other particles?
Yeah,
like
all other particles were detected.
Before the standard model was written?
No. No. If you read, I asked you as a homework, I gave you to read the first chapter in Griffiths. It's a historical overview, and it describes how, you know, during starting from the 30s, 40s, 50s, 60s, every time new particles were detected, including in the 70s. The charm and then the strange quarks, and, you know, new particles made of them, and it took a while for people to accept the quark concept. So we'll discuss that. It took, and then the tau, I think, was detected in 1996. It took roughly 80 years for all the particles to be detected, for the standard model to become complete. To me, this is one of the problems of the standard model, that at the moment, it does not contain any new particles that have not been detected yet. It does. There are these, problems that I pointed, showing that it's incomplete. But one of the problem is that we have not detected any particle that cannot be explained within the framework of the standard model at the moment, to the best of my knowledge. And the standard model does not predict other particles that were not yet detected. I have to say that, again, with a grain of salt, because there are theories beyond the standard model, right? Because theories such as supersymmetry do predict new particles. For every fermion, there should be an extra boson, etc. So these are extensions of the standard model. The classical standard model, we got all the predictions of all the particles made. Okay, we may or may not, I'm not sure how much time we'll have, discuss, I told you that already, models beyond the standard model. So in the standard model, particles are divided into three basic categories. So category number one is what's called the fundamental fermions. Right? This is what we call matter particles. These are the basic ingredients of matter as we know it. They all have spin 1/2. Another thing maybe I should say, about the particle that you asked previously, right? One of the extensions of the standard model would include gravity. And then there is a particle which is known as graviton. I see that Ofek is very happy about that. Again, this is not part of the standard model. It's an extension of the standard model. And it was never detected, but if it exists, then there are predictions to some of its properties. Okay, and that's, again, remember that gravity is not part of the standard model. Okay. So we have the fundamental fermions. How many are there? Do you know?
6.
How many?
6.
12.
12.
12. Okay.
Total 12. Then there are the interactions between the fermions. right? Again, these result from certain symmetries, and they are transmitted by spin 1 bosons. These are known as vector bosons or gauge bosons. So there's going to be a lot of jargon today. So the electromagnetic interaction this is called, the theory is the QED. What is the vector boson responsible for transmitting the electromagnetic interaction between fermions?
The photon.
The photon, that's right. This is simply the photon. Then there are the weak interactions. Right, the theory is called electroweak. Now, in fact, both of these are today unified under what's called electroweak interactions. What are the transmitters, the weak interactions? What vector bosons?
Z and W.
Very good. It's a W and a Z. And there is a strong interaction. And the theory behind it is called the QCD, quantum chromodynamics. And what is the mediator, the gauge boson that mediates that?
Gluons.
The gluons, very good. It's called the gluon, G. Okay. As I said, gravity is not part of the standard model. Because there is still no complete quantum gravity theory. Except maybe strings, but again, not a string theory. Yeah? Question? And then the other particle, so we're still describing the, is there any question?
תטא זה לא? לא, תטא זה כאילו ציר Y שזה לא.
Sorry?
שזה לא.
Ofek, if you're having discussion, then please turn on your microphone. Okay, the other part of the other ingredient of the standard model is the Higgs particle. It has its own category. It is a spin 0 particle. So a spin 0 is boson, so it's a scalar. And it has a mass of 125 GeV that we know today. Now it is related to the process of asymmetry break in electroweak theory. And this is the process in which all particles acquire mass. Okay, so without the Higgs, all particles would be massless and all will travel at the speed of light, and the universe would look very different than what it looks for today. Okay. So let's start with the fundamental fermions. We said that there are 12 types of fundamental fermions. And these 12 types have names. These are called flavors. Right? Now, from the 12, we have 6 flavors of quarks. And 6 flavors of leptons, which I haven't described what are leptons or quarks. But I will define it very shortly. I'll define it now. Leptons are particles that do not interact via the strong interactions. Right. Now, okay, 12 is quite a large number, but again, it follows from a certain symmetry. And what I read, at least, in the textbook, they said that nobody still fully understands this, this symmetry. And people who work with that are called flavor physicists. Now, the flavors, the 12 flavors of the fundamental particles come in what known as 3 generations, known as families. So let me write it down. The flavors of the fundamental fermions come in or appear, the word, appear in 3 generations, which are also known as families. So in each of the generation, each generation, there are 4 particles. And these are the neutral lepton, which is the neutrino, the charged lepton, an up-type quark, and a down-type quark. So I made a small table that summarizes these particles and the basic properties, which are charge and mass. So we have generation 1. Let's see the table. Generation 1, generation 2, generation 3, and charge. So for the first generation, the neutral lepton is the neutrino electron. And the mass is not zero, but very, very small, less than 1 electron. The charge is 0. For the charged lepton, this is what?
Electron.
The electron, of course, the electron. So the mass of the electron is 511 keV. Maybe better to write it in MeV, so this is 0.5. 511 MeV. The charge, of course, is -1. The up-type quark is what?
Up quark.
Up quark, right? The U. Up. The mass of the up quark is 2.3 MeV. What's the charge of the quark? Do you happen to know, any of you?
Positive 2/3.
Very good. This is Q is 2/3. And the down type quark obviously is the down quark. This mass, which is slightly above, but quite similar, it's 4.8 MeV. And the charge is -1/3. In the second generation, why? Why are you doing it to me? So the neutral lepton, now it gets more interesting. What is the neutral lepton?
The mu neutrino?
Very good. This is the mu neutrino. And again, the mass is nearly 0. Mass of the mu neutrino is nearly 0. Its charge is 0, of course. The charged lepton is the muon. Now it's much more massive. It's 106 MeV. So this is 4.8, right, and 2.3. So it's nearly 20 times heavier than the down quark, right, and 200 times heavier than the electron. And then the up-type quark, you know what it is?
Strange.
Nearly, it's the charm.
Ah.
Or the charm. And the mass is much heavier. Now the charm is 1.28 GeV. And the down type quark is the strange indeed. And the mass of the strange is 95 MeV. And of course, the charge of the muon is -1. The charge of the charm quark is +2/3, and the charge of the strange quark is -1/3. In the third generation, the neutral lepton is the neutrino tau, the tau neutrino. And again, the mass of the tau neutrino is smaller than electron volt, chargeless. The charged lepton is the tau, whose mass is 1.78 GeV. So again, it's nearly 200 times more than the mass, 20 times more than the mass of the muon. And then the up-type quark is the top quark, whose mass is 173 GeV. So again, look, there are the jump here, right, from 1.28 GeV to 173. This is nearly 150 times more massive. That explains why it was the last quark to be detected. Then the down type quark is the bottom quark. So B, which stands for bottom. Of course, these names are just arbitrary chosen. So not sure what, well, why they're chosen, and the mass is lighter. It's 4.2 GeV. So these are the 12 fundamental leptons. Now these are fundamental fermions. Sorry. Right now the dynamics, being a fermions, they are described by the Dirac equations. Their dynamics is described by Dirac equation, which we will learn. This is the equation for relativistic quantum mechanics. Now, an important consequence of the Dirac equation is that it predicts that for every particle, so for every fermion, there must be an anti-fermion. There must be an antiparticle. The Dirac equation predicts that for every fermion, there must be an antifermion. So it has the same mass, but opposite charge. When we say charge, I mean not just the electromagnetic charge, but all the charges that it carries. Same mass, but opposite charge. So the antiparticles of the charged leptons the positron, the positive muon, and the positive tau. Now the antiparticles of the neutrinos here. Antiparticles of the neutrinos they are denoted with a bar on top of them. So this will be the neutrino electron bar, the neutrino mu bar, and the neutrino tau, or the tau neutrino bar. And the same, the anti-quarks, they are denoted with the same letter as the quark, but with a bar on top of them.
Is there a charge that's opposite for an antineutrino and the same neutrino if they're both neutral?
Yes, because they carry leptonic number. I'll discuss that. I don't know if today or next lecture. We'll discuss the different charges and symmetries that the particle carry. So that's why when you have a decay, there is only a certain type of neutrinos that you can see, because leptonic number is conserved. So for the antiquarks, there is the same letters but with a bar. So U bar, up bar, down bar, strange bar, charm bar, bottom bar, and top bar. This is how they are denoted. So opposite charge is opposite charge of all interactions. Not just the electromagnetic one. Okay. Now let's talk a little bit about the interactions. So the particles interact with each other via the four fundamental forces: gravity, electromagnetic, strong and weak. So gravity is very, very weak. It is much weaker, many orders of magnitude weaker than the weak interaction. And we normally neglect it when we discuss particle interactions. So gravity is normally neglected. Simply too weak. Too weak. So the properties of the 12 fundamental fermions are categorized by the type of interaction that they experience. So I make another table that summarizes the interactions. So the table goes like that. If this is the fermion. And this is strong. This is electromagnetic. And this is the weak. So for the neutrinos, right, the electron neutrino, muon neutrino, and tau neutrino, are they going through the strong interaction?
No, they're not quarks.
No. What about electromagnetic interaction?
No.
No. What about the weak interaction?
Yes.
Yes. It's the only interaction that they obey. Now for the charged leptons. Right, the electron, muon, and tau. Are they going the strong interaction through? Are they interacting via the strong interaction?
No, only quarks, you said.
No. What about electromagnetic interaction?
Of course, they're charged.
Charged, of course, right? What about weak interaction? Very good.
Yes. It's,
What about the quarks? Are they interacting via the strong interaction?
Yes.
Yes, they do. What about electromagnetic interaction?
Yes.
Yes, they do. What about the weak interaction?
yes.
Yes, they do. Very good. That's how it looks like. So obviously a fermion is subject to the electromagnetic interaction if it has an electromagnetic charge which is different than 0. And similar to that, it is subject to the strong interaction if it carries what's called a strong charge. So fermion is subject to the strong charge, to the strong interaction, if it carries a strong charge. You know how we call this strong charge?
The color?
Yeah, this is called a color. Sometimes it's called a color charge. Of course, it got nothing to do with the color that we're used to from real life. Now, the color appears in 3 types, which we call R, G, and B, red, blue, and green. So clearly from the table, all particles are subject to the weak force. So they carry the weak charge, except the neutrinos. All the other 9 particles are subject to the electric interactions. So the electric interaction is a framework of quantum electrodynamics. So it works for all these 9. Now, the quarks, just to say a word about the quarks. Right, these are the only particles that carry the QCD, it's called quantum chromodynamics. QCD equivalent of the electric charge. Which is known as the color charge. Now, because of the nature of this color charge, quarks cannot be observed as free particles, but they're always confined to bound states. Okay, and these bound states, they make 2 types of particles, the hadrons and the mesons. Mesons is a pair of quark-antiquark, and a combination of 3 quarks known as hadrons. So let me just write it down. Because of the nature of QCD interaction, quarks are never observed. As free particles. But as bound states. Making particles as hadrons. For example, the proton how do you make a proton?
Up and down.
Up, down.
Up and down, made of 3 quarks. And the neutron?
Up, down, down.
Sorry?
Up and 2 downs.
Up, down, and down. That's right. Now, interestingly enough, the proton and the neutron, hadrons are divided into baryons and mesons. The hadron is the general name of the bound state of the quarks. Now, the proton and the neutron, these are the only hadrons that exist as stable matter. These are the only ones that you find in nature, in the kernels of atoms. The reason is that they are made of the lightest quarks, which are in the ground state. So it's the lowest energy bound state. Right? You can make other hadrons, but what will happen is that they will decay. So they're not stable. So we said a lot of jargon. So particles that do not carry the strong force are known as leptons. So leptons, again, this is some Greek word. It's called sin or something. Collective name for all particles that do not carry a strong force. In fact, there are only 4 stable leptons, which are the electron and the 3 neutrinos. All other leptons are not stable, they will decay. If you get yourself a muon, it will decay quite rapidly, simply because they're heavier. Okay, now questions. A lot of jargon, just to make sure that we all talk to the same language. For introduction. Any questions? Okay, no questions. I want to speak about the fundamental forces. So now I'm going to tell you something which is quite deep, because it lies in the heart of the quantum field theory in general. Right? When you think of a classical electromagnetism or quantum mechanics, it doesn't matter, right? But let's stick just for the sake of discussion about electromagnetism. Then the electrostatic force acts on a particle, described in terms of a scalar potential, right? So the particle moves in the potential well, right? It can be attracted, it can be repelled, depending on the charge, right? That's how we describe it. And that's how we, when you do classical electromagnetism, you say there is a particle moves in the potential, Coulomb potential of another particle. They can repel each other or attract each other, right? Am I going too slow, by the way? I'm asking for your feedback at this moment.
I think it's appropriate.
You think it's appropriate? Okay.
I agree.
Okay. Now, what's the problem? What's the problem with this description of the force? Right. We said actually in first year, we learned that in first year, a force can be derived from a potential if it's a conserved force, right? Well, what's the problem? There is a very deep problem in here. And the deep problem, before I tell you the answer, does anybody wants to try? Nobody? Come on, guys. Well, what's the problem with this description?
Is it the problem with the time it takes? So, if 2 electrons are far apart, they feel each other instantaneously, or?
Very good. Excellent. 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 This is the right answer. It violates relativity. Right? According to relativity, nothing travels than the speed of light. All right? And this prescription essentially assumes that there is a force, which is, what is it? It's information about the change of momentum. It travels at infinite speed between the 2 particles. Right? This is what's this is called the action at a distance. But this is not allowed according to relativity. Okay, in relativity, no signal can travel faster than light, point. Okay, so let me write it down. So this is the first problem. There is a second problem. Think of it for a second while I write it down. In classical EM, in classical electromagnetism, the electrostatic force between particles is described in terms of a potential. However, this violates relativity, right? Nothing travels faster than light. What's the other problem? Any suggestion?
Possible irrigation variance for many potentials that.
No.
Okay.
It's non-local. I'm not sure if that's part of the first one. It's non-local, which is
the first one. It's it's action. It's an action at a distance, which is non-local. It is part of the first one. What is the second one? Think of it from an experimentalist point of view. This description does not incorporate any interaction that enables the production or destruction of particles, right? You cannot describe the emission of photon. You cannot describe the creation or annihilation of pairs, electron-positron pairs. And we do see this happening, right? So this prescription does not allow the creation or annihilation of particles. Right, but particles are produced, right? Photons are emitted. Pairs are produced in laboratories and in cosmic rays.
What do you mean it does not allow? I don't understand this claim.
Sorry, I could not hear you very well.
I don't understand the claim. Why does a potential not allow the creation of particles?
Because when you describe an interaction between two particles via potential, you just, they just change the momentum. But there is nothing in the formalism that enables you to write down the creation of new particles. Let's say you have interaction between electron and a proton.
Okay, so it's not included in the theory, but it doesn't.
It's just part of the theory. You want a theory that under the same framework will enable you to describe what you're seeing. And you are seeing.
It's not that there's something wrong with the potential, it's just that it's incomplete. The first point is there's actually something wrong with the theory in the first point.
No. You cannot, when you say incomplete, means you can add to that an extra layer.
Yeah, why not? Why not just, say there's potential and I'll add, scattering interactions where an electron and a positron come in and a photon comes out. I added an extra layer.
I understand the question. I don't know of any such an extension, and I do not see any natural way of doing that. I don't know if it can be done in the framework of the description of a potential. To give you a fully honest answer, because I never thought of that deep enough, possibly.
I think what you mean is that the description just talks about it happening. It's not mediated through any way.
No, the idea of mediation, again, this is something which is built in quantum field theory. Again, the quantum field theory essentially came in order to solve these two problems. There is a deep theoretical problem here, which is stated right here, the fact that it violates the laws of relativity. Right? This is something which is theoretically unacceptable. If you want to accept the relativity as correct, then you cannot have a theory that violates it. And the second point is that there is nothing in the theory, as I know it. I don't know if anybody tried to write any extension of the theory as is, I doubt, but maybe somebody did that, I don't know, that, that enables you to incorporate naturally within the theory the possibility of creating or annihilating particles. Right? Particles are not annihilated, right? Particles, you know, if you think of it in terms of potential, right? Then if you have an electron and positron, they could come together and they could stick in a plastic collision, but they cannot disappear and produce new particles. This is not allowed in this theory. Right? So in the quantum field theory framework, there is a solution, right? So the quantum field theory was invented, in fact, exactly to solve these problems. Okay? So within the framework of quantum field theory, the interaction between particles is mediated by these spin 1 or vector bosons, right? So the force is described in terms of a particle exchange. So there is no longer this concept of action at a distance. It's just being thrown away, right? So let's write it down. In the framework of quantum field theory, interaction between particles is mediated by spin 1 bosons and there is no longer action at a distance. So, for example, the electromagnetic interaction, right, between two charged particles will be described as if it's mediated by what's known as a virtual photon. Now, what is a virtual particle? So let's write it down and give you the definition. E.g., right, electromagnetic interaction between charged particles is mediated by the concept of a virtual photon. So it's not a real photon. So a virtual particle is a quantum fluctuation which exhibits some of the characteristics of a real particle, but its existence is limited by the uncertainty principle. We cannot see a virtual particle by itself. And moreover, a virtual particle does not obey the energy momentum relation of Einstein, which we just saw last week. So m squared equal E squared plus P squared is not obeyed by a virtual particle, right? The technical term for a virtual particle would be off the mass shell. Let's just write it down. And a virtual particle is a quantum fluctuation which exhibits some of the properties of real particles. but its existence is limited. By the uncertainty principle. No, it does not obey the energy momentum relation. Like m squared is equal E squared minus P squared. This is not obeyed by a virtual particle. We say the technical term is that it's off the mass shell. The whole point is that to be consistent with special relativity and to ensure that in each interaction, the form momentum is always conserved. Okay? Now, because it's a quantum mechanical in nature, then each time there is an interaction, the momentum exchange can be both repelling and attracting, and you can exchange quantum numbers. So spin can change, charge can change, right, as long as it's conserved. So for example, if you want to describe interactions between two electrons, right? This is mediated, there are two charged particles. This is mediated by the exchange of a virtual photon. Right? Then we write it, what's known as the Feynman diagram. So Feynman diagram, I'm going to describe to you exactly all the steps, but right now it's just an example. So the first time that you're seeing it, presumably. So you have an electron. So in a Feynman diagram, the first thing to realize is the time flies in this direction. Time always flies from left to right. In very old textbooks, it is not like that, but right now all textbooks are standard. Time flies from left to right. Electrons, leptons in general are described by straight lines with an arrow that doesn't point the direction of the motion, but points to the direction of the charge. So we have an electron that emits a photon. Photon is always described by a wiggly line and continues on its way. And then we have a second electron that comes, interact with this photon, and goes its own way.
Is this the direction of the charge or of the negative charge?
Of the charge. It will come with a minus sign, but essentially it's a charge. Okay, you're right that it can be a bit confusing. Right now it's a charge. Don't confuse me more than needed. Okay, so here, the way I plotted it, you have the first electron, the upper electron emits a photon. In each vertex, the form momentum is conserved. So the form momentum before here is equal to the sum of the form momenta at the end. This form momenta of the photon carries with the photon and interacts with the second electron with the lower electron. Of course, there is the opposite, in which so we have a second Feynman diagram in which the down electron first emits a photon, which then interacts with the upper one. So you have a lower electron, right? emits a photon. And the upper one then interacts with this photon and goes its own way. So what is plotted here is a scattering process. Two electrons get close to each other, they exchange a photon. This is a virtual photon. We cannot see it. This virtual photon is what mediated the exchange of momentum and possibly energy between these two electrons. Right? Again, these are independent ones. Okay. Now, so this photon really is what transfers the momentum between the upper electron and the lower, and then here between the lower, between the lower and the upper. And this transfer of momentum is essentially what we call a force. Right? Each one, there is a momentum exchange between the two particles. So since the momentum changed, we say that the force acts upon them. Right? Now in quantum field theory, we can do these tricks because the basic entity is a field. Right? In QFT, just for general, we talk about fields. Right? And the fields fill the entire space. And a particle is nothing but an excitation of the field. Right? The first excited mode of the field is a particle. Second excited is two particles. Quite simple. Easier said than done. When you start actually understanding how it works, it's not as simple as I describe it, but essentially that's what it is. Right? Now, we said we have three fundamental forces. So each one of them is described by an exchange of one spin one force carrying particle, which is known as gauge bosons. Right, so first, questions about that? Okay. I know that I'm sort of running out of time. I'll take a few more minutes from the time, and that's it. So each of the three forces relevant to the standard model is described by an exchange of spin one carrying particle which we call the gauge boson. So we said that in the Feynman diagrams, each one is described in a slightly different line. So the spin one photon right? The one we like and love and know, right? It's the gauge boson for the electromagnetic interaction. So this is the gauge boson for the QED. It's massless and photon is 0. This we know. Well, best measurements get to 10 to minus 15 electron volt atom. And the description is with a wiggly line like that. Now the weak interaction what is where do you see the weak interaction? Where is it manifesting itself mostly in nature?
Decay.
Decay. Which type of decay? You have various decays.
Beta decay, right?
Beta decay. Very good. This is a radioactive decay. Right. This is the beta decay. What is a beta decay? It's a neutron, which is a down quark, goes into a proton. So one of the down quarks turn into an up quark, but then you have to conserve the charge and you have to conserve the electronic number. So you end up with a neutron decaying into a proton, electron, and an anti-neutrino electron. You see that in the beta decay, and you see that in nuclear fusion. This is mediated by the charged W boson, W plus minus bosons, and the neutral Z boson. The mass of the W bosons is about 80 GeV, to be quite precise. And the mass of the Z boson, it does not carry any electromagnetic charge, is slightly higher, it's 91 GeV. Now, in some textbooks, now here I see the different presentation. In some textbooks, it's also weekly. Some other it's just dashed line. I think the dashed line is what I'm familiar from, but I see that in recent textbooks, some are using this weekly pattern as well. I'm not sure why. Trying to see if I got anything. Don't know why. For the strong interaction, we have force-carrying particles, which are known as gluons. These are massless, and gluon is equal to 0. However, you know, for the QED, for the electromagnetic interaction, we have only single mediator. This is the photon. For the weak interaction, we have 3, the Z and the W. For the strong, we have 8. So we have 8 total gluons. There are 8 different gluons. And the reason why there are 8, because each is carrying a different color charge. All of them are massless. We'll speak about that thoroughly later. The way they are being described is by like a spring light. Now, again, all these interactions mathematically can be shown. I'm not sure if we will have time to show, or if it's part of the syllabus of an introductory course to particle physics, that they all originate from symmetry groups. And all interactions originate from symmetry groups. How, then we'll discuss that down the line. Okay, I already also mentioned, once gravity is included, then we have an extra particle, which is the gravity extra boson, to be a spin 2 actually, which is called the graviton. If gravity is included, then we have in addition the graviton. I'm sorry to disappoint Ofek, but I'm afraid that we're not going to discuss gravitons in this course. And different than the photons, the Z, W, and the G, and the gluon, do carry charges, right? Not just electromagnetic charge. There are other types of charges, like the color charge, right? they have the charges of their specific interaction. There is a weak charge, etc. So they are affected directly by the interaction. So W, Z, and G do carry charges, but not electromagnetic charge. Well, the W plus minus do carry electromagnetic charge as well. All right, I think this is about the right place to stop. I've made much less than I was hoping to accomplish this lecture, but I don't really care if we go through everything. I care much more about that you understand what we are talking about. I don't think these are, I said anything conceptually very hard. I just gave you more bits and pieces of quantum field theory and gave you some a lot of jargon and a lot of to give you some material to work with or to think about. It will, next lecture next week will continue along these lines, and then we'll go deeper into some of the processes involved. But I'm not sure if we'll finish everything I have to. Well, it's just giving you, still it's in the introduction part, and there are plenty of introduction things to speak about. Feynman diagrams, the weak interaction, I said that the ground state, there are non-ground state, excited state particles, the rho, the delta, and some other things. So we'll discuss all that, make a little bit of order. But this will be next week. Any questions?
I have one.
Yes, please.
Is it it's probably possible for virtual particles to transfer negative momentum or negative energy?
Correct. Yes, they can carry negative momentum, negative energy, unlike real particles.
Mm-hmm.
Yes.
How does that? Maybe it's for another lecture.
What is the question? Maybe.
In the Venn diagram above, we see right. They have basically the photon goes from one electron to another, and it can be viewed as if they're separating. So the electron takes it gets upward momentum, and the photon gets downward momentum, and that's why it travels down to the other electron.
Okay, yeah.
If it had upward momentum, how would it reach the other electron?
Okay. This is a completely cartoonist version. It is not describing, as opposed to what it looks like, it is not describing the spatial location of the particles.
Mm-hmm.
Okay. It's a completely, and this is not the only thing that happens. We will discuss Feynman diagrams, well, some introductory to Feynman diagrams next week. You see, this is one term in an entire infinite set of possibilities of how particles can interact with each other. This is the first order term, right? This is the simplest one. It does not describing what happens in real space. It is just to tell us what type of, it is just describing the interaction itself. It is really just a computational tool. Really, for this, we really have to learn quantum field theory properly, because what we really have behind here is a very long integral with connects the four momentum of the two particles that interact with each other, and the delta function that ensures that there is a conservation of four momentum.
I see. So the cartoony diagram won't make sense as a diagram, but the math behind it will.
Yes.
I see.
Yes. The only thing to think of, which, well, we discuss that next week maybe. I'll introduce you to Mandelstrom Variables. The difference between the T diagram, which is a time diagram, and an S diagram, which is a space diagram. But don't take it as describing what really happens in terms of space. It's really a computational tool to interact essentially the probability of scattering and the exchange of momentum between particles in the scattering process. Okay, it's an extremely, extremely useful tool. Again, when you learn quantum field theory one day, you'll see what was before that, what type of nasty integrals people have to solve, and you see how much computational time this diagram save. And this is a real simple one. I mean, we didn't talk about exchange of two photons, exchange of a photon that creates virtual pairs in the middle, right? We could have that as well. There can be many, many things here, much more nested than you think. And everything is encapsulated in this tiny, beautiful, pictorial diagrams. And just take it as is, right? Describing what you see here is is the way we describe interaction between particles. Two electrons come together. They don't interact via the potential of one another. They simply exchange particle. This exchange of particle is what ensures that there is a conservation of the form momentum at each step of the process. They can exchange one particle, two particles, actually infinite number of particles, and then we need to do summation over infinite options, and then we have to renormalize everything back to something that gives us a finite result. It's all done, but we'll discuss that a little bit more well, not really in depth, but I'll give you some sort of introduction to that in the next lecture, because we're already out of time. Now, question: how many of you have seen Feynman diagrams in their lifetime before? I'm seeing two hands raised. Not just the diagram, actually seen how it really works. Yeah, so you know what I'm talking about when I'm talking about nasty integrals, which can fill it several lines and plenty of delta functions. So I'm saving you all that. But just that you know that it's not just a nice tool. It's a very, very important tool that saves you a huge amount of calculations. And I actually, again, I did teach quantum field theory in the past. So I actually do that there. It's, to my opinion, it's beautiful. It's heavy in math, but it's very structured. Here we simply don't have the time to give you the full description of how it works, because it will be half the semester. All right. So I'm just telling you what it is and how to work with it. Okay, guys.
Thank you very much.
Thank you, and see you next week. We're going slightly slower than I was hoping. Nothing is terrible. I would go as you tell me. If I feel that you want me to go faster, I'll be happy to go slightly faster. I don't think there is a need to go slower than that. But, you tell me. Have a nice weekend, I guess.
Remind people there's an astral seminar in 1 hour and 15 minutes.
Okay, but this is not related to this course. If you're interested in an astro seminar, you can join. You heard of the advertisement, but that's got nothing to do with the contents of this course. All right. Bye-bye. That was